Thank you. Hi, everyone. Good evening, good afternoon. I'm Avinash Chaturvedi, a second year PhD student at the European Southern Observatory in Garching. And today I'm going to talk about kinematical signatures of interaction between Fornax cluster galaxy. And my supervisor is Mikhail Hilker, and my collaborators are Glenn van der Ven and Nicola Napolitano. So in coming few minutes, I'm going to follow this outline. First, I will be talking about introduction, data analysis, and then finally concluding my talk with the results and summary. And here you see the beautiful image of the Fornax galaxy cluster. So let's get started and try to understand that why we are focusing on a Fornax cluster. So my PhD deals in understanding the Fornax cluster, like its formation and evolution. If you look for the galaxy clusters, then they are the most massive gravitationally bound objects. They follow the lambda CDM model. And particularly for the Fornax cluster, it's one of the nearest and densest cluster. So it's provide a chance, opportunity to study the galaxy clusters in the detail. And specifically for Fornax cluster, some of the recent studies, like the photometric and spectroscopic studies, have confirmed that there are stellar and tidal streams between its central and its neighboring galaxies. So this signifies that the cluster, this Fornax galaxy cluster, is quite active, and this makes it quite interesting to understand that how does the galaxies assemble and how does the galaxies interact in a cluster, specifically for Fornax cluster. So this is what we know about Fornax cluster, that it's one of the nearest densest, and there are confirmation of stellar and tidal streams between its central and its neighboring galaxies. But still there are pictures which we are missing, like mass assembly. How does the individual galaxy assemble themselves in a galaxy cluster? And for understanding this, we are performing the dynamical mass modeling of this galaxy cluster. And since I mentioned that people have, with their studies, they have find the stellar streams. Basically, these are the intra-cluster objects, not bounded with any galaxy, but lying in between galaxies. So it's also interesting to see how does the presence of intra-cluster objects will affect the dynamical modeling or the mass modeling results of the Fornax cluster. So this is where my PhD starts, and we are using, like, our goal is to perform the dynamical mass modeling of the Fornax cluster, and for this we need the kinematical tracer, the potential tracer of the Fornax cluster. And in my case, I'm using global clusters as the kinematical tracer of the Fornax cluster potential. So global clusters are the bright objects, and they can be easily detected in the outer halos of the galaxy cluster of a galaxy, rather than in comparison to the filled stars. So in my case, the spectroscopy comes from the WIMOS multi-object spectroscopy. And here in this plot, what you see is the central 1 square degree coverage of the Fornax cluster, shown in the red box. And this data set, and in total there were total 25 pointings of the WIMOS, and this provides us roughly 5,000 spectra. So roughly 5,000 spectra coming from different slits. So this data set was already analyzed by Bode et al. In 2018, but the recovered number of global clusters in their study was quite low. It was like 10%, even less than 10%. So this was one of the strong motivation to reanalyze this data set. And also there was some technical issues with the pipeline, with the ESO reflex pipeline. So my first goal when I started this was to look for the improvement in the pipeline. And the issue was like you have different individual exposures, and previous pipeline has this issue that the final stacked spectrum showed some broadening. Here in this lower plot, what I'm showing you is one of the reduced spectra with individual spectrum, and the black line is the stacked spectrum coming automatically from the pipeline, shown in the calcium triplet region, 3 strong absorption feature, and the black line shows the final reduced spectra. So we did this for several spectrum, and we didn't find any significant broadening as it was seen in the previous pipeline. So these were two main motivation to reanalyze this data, because of low recovery of global clusters and improved version of the pipeline. And after this, we used a bit better methodology to find the radial velocity of global clusters. So for measuring the global cluster radial velocity, I used PPXF. It's a Python implemented tool which uses the absorption feature of a spectrum to find its line of sight velocity and other higher order moments. So here what you see in the plot in the left side is one of the fitted global cluster spectrum. The global cluster spectrum is shown in the black and the fitted model spectrum is shown in the red one. And the different blue bands shows the regions which are masked out from the spectral fitting. On the right side, you see the major absorption features like H beta, H alpha, calcium triplet. So we use these absorption features, the zoom in absorption feature, for visually identifying and selecting the bona fide global clusters. But before going, like how many global clusters we we got from this data analysis, it's good to see that how robust is our velocity measurement. So in some of the pointings, the global clusters were observed twice. So this gives us a way to see how robust is our velocity measurement. So here in this ever plot on the x-axis, you see the line of sight velocity of the global cluster plotted against its g magnitude. And these the black dot and the red star shows the radial velocity of the same target observed twice in a different VMOS pointing. So all our measurements lies within the 1 sigma uncertainty. So this was quite a strong proof that our radial velocity measurement is robust. And here in the lower plot, I'm showing you like some of the targets were also covered in the previous literature velocity comparison, literature measurement. So this also gives us a way to see how is our velocity measurement in comparison to literature. So here in this plot on the x-axis, you see the velocity from my work, and on the y-axis is the velocity from the literature measurement. So we got almost one-to-one correlation, and the outlier points are mostly coming from the previous study, which I will explain later. So this was the first verification that our method is working, and it's a kind of robust in terms of determining the velocity. And after this, let's go to see how many global clusters we detected. But before this, I just wanted to show you the plot coming from the Pota et al. Who analyzed this data. So here what you see is the global cluster radial velocity map, color coded with its radial velocity. Here each dot represents a global cluster and the cross represent the major galaxies or the Fornax. The central one is NGC 1399 and its neighboring galaxies. So they had like 387, and after our analysis, the plot is we have total detected 777 global clusters on the same data set. And now we have much uniform sample. But the interesting thing is, if we combine this with all the literature velocity measurements, then the plot looks like this, and we are able to characterize the kinematical features of the intracluster regions. And here, you can see clearly that in between, like in this galaxy and here, you can see the stream of global cluster. But maybe this is more clear in this plot. So here, what I'm showing you is the radial velocity map, or the global cluster phase space distribution, color coded with its radial velocity, overplotted. Can you hear me here?
Yep.
Yes, yes. So here it's the radial velocity map of the global cluster, or the phase space distribution of global cluster, overplotted on the photometric surface density map. So here the white color represents the photometric surface density map coming from the study of Cantiello et al. So what you see in the white color is like just the surface density map of global cluster, and these are the photometric regions which people have discovered previously, and they call these regions as the intracluster regions, intracluster global clusters lying between galaxies and not bounded to any galaxy. So our work gives the kinematical confirmation to these intracluster regions. So this is the first important result, that this produces one of the most extensive radial velocity catalog of global clusters belonging to the Fornax cluster. After this, it's interesting to see what kind of global clusters are distributed, like what kind of global clusters are in the center or in the substructure regions. So global clusters comes in two variety: metal poor and metal rich. Metal rich global clusters or the red global clusters, and metal poor or the blue global clusters. So to divide the sample into the metal rich or metal poor global clusters, I use the color magnitude diagram from the in G minus I and U minus R, and then fitted a bivariate Gaussian over the sample, and then divided the sample into the red and the blue global cluster. So here, this was I was talking about this right plot, and then in the sorry, left plot, and in the right plot, what I'm showing you is the phase space kinematics of the red global clusters and the blue global clusters, plotted against the radial velocity, plotted against the projected distance from the central NGC 3099 to the as we move outward in the galaxy cluster. So here the red global clusters are mostly centrally concentrated, and they are mostly concentrated over the near in the vicinity of the galaxy, individual galaxies, and they follow the systematic velocity of the whole cluster, like at least in the central area. But if you go to the blue global clusters, then you see that they are covering all these regions which where we don't see the red global cluster. So basically the blue global clusters are widely spread, and they show irregular and complex pattern, although it's not very easy to see in this plot. But you can see that here the concentration of the global clusters here is larger than in comparison to here, and I will show you that why it's different in the coming slides. So this was the thing, that the red global cluster follow the systematic velocity of the whole cluster, whereas the blue global clusters show complex and irregular kinematical pattern, and they cover the regions which are not traced by the blue global red global cluster. Finally, it's also interesting to see how the red and blue global clusters are distributed in the phase space over the photometric surface density map. So here I'm showing you the red global cluster phase space distribution on the photometric surface density map, and the different major galaxies are labeled in the green box. So you can see that the red global clusters are mostly concentrated on the central galaxy system, and also within the vicinity of the other major galaxies. But the interesting thing comes when we go for the blue global cluster. So the blue global clusters are mostly tracing, like here you can clearly see the substructures. Here, this chain and this part. So these are the four different subregions, substructure regions. So the blue global clusters are mostly dominating these substructures. So with the kinematical information, this is quite important for the future dynamical modeling, because now we are also giving a kinematical characterization of these substructures. So this I see as the second most important result, that with our catalog and with our this work, we are able to characterize the substructures of the Fornax cluster. And after this, before, like, we will use this data set for our dynamical modeling work, but very beginning picture of our we can have the like idea of the dynamical modeling from this kinematics by looking at the velocity dispersion profile. So this gives us the idea, like how how are the kinematically global clusters are distributed. So here, it's just the velocity dispersion profile of the global clusters. Shown in the red dot shows the velocity dispersion profile of red global clusters, and the blue shows the blue global cluster dispersion profile. And whereas the black line shows the total dispersion profile. On the x-axis is the projected distance from the central NGC 3099. On the y-axis is the RMS velocity dispersion. So you can see that and here the dotted line represents the position of different galaxies. So one thing was quite clear, that after 10 arc minutes, we noticed that the dispersion profile was almost got flattened, but it was fluctuating because of presence of individual galaxies like here, like here. So this signifies a region from where the cluster potential is dominating, not the central galaxy, but it's the cluster potential dominating. And to see this clearly, we thought to do the same work just with the intra-cluster global clusters. And for this, I made a cut in the Phasor space, like selected a region outside the two effective radii or the four effective radii of each individual galaxy, and then performed a velocity cut. And after this, we can get a velocity dispersion profile, something like this. So here, it's like for the intra-cluster, we almost see that after 10 arc minutes, the velocity dispersion profile flattens. So this signifies that after 10 arc minutes is the cluster potential which is dominating. So this is the like third and final results from my talk today. And then finally, my conclusion that our work has produced one of the largest kinematical catalog of global clusters. We give the kinematical confirmation of the intra-cluster global clusters. We notice that the red global clusters are centrally concentrated on NGC 1399 and on other major galaxies, whereas blue global cluster dominate the intra-cluster region of the Fornax cluster. And this data set will be crucial to perform the dynamical modeling of the Fornax cluster. And that's all. Thank you.
Thank you very much, Avinash. So we have time for questions now. If you have a question, please raise your hand. Okay, seeing no questions. So I have a question. We actually submitted recently a paper about a month ago looking at the spatial distribution of the global clusters in galaxies in the Fornax cluster. And we find structures in the distribution of the global clusters, which we attribute to past interactions, similar to the structures that we saw a few years ago in Virgo galaxies. So it would be very interesting to compare the location of your filaments with the location of the structures that we find when our papers are more evolved and published.
Okay, I would be very happy to see it.
Yeah.
I didn't know that it's also on the Fornax cluster. I'm very excited to know this.
So this is work led by Rafael Dabrusco from CFA. So
yes. Yeah. Okay, I will see. And then he has these papers, and also like in the past, where they talk about this discovery about the substructures.
Exactly. Yep.
Nice to know this.